forgot to hit record. Okay, so putting the polysaccharide gums in are typically because of either thickening or gelation. We want one of those or both of those characteristics. And then polysaccharide gums also have a lot of secondary functions that are listed down here at the bottom. We already went through this last week, but these gums can be very difficult to dissolve because when we put those gum particles into water, they will swell and they can stick together. And if those little particles stick together, it's really difficult to get those out of the product. And so you get something called fish eyes, which is very not desirable. So what you can do, basically what you want to do is separate the particles as you're adding them. So a common way to do that is with something called a funnel disperser, and that's the picture shown here. So this funnel disperser has the gum mixture up there in the funnel. And it's being fed through this hole very slowly. And there are air currents that are coming in right here. And that will basically separate all the particles by blowing them around. And then the water will come in and they'll be combined together here in this cyclone area, and then come out the bottom. And so when we separate them by air using this funnel disperser, then we have enough room for them to swell. Yeah. So what would the fish eyes look like? They just look like particulates of like a gummy substance. And essentially what they are and what makes them really undesirable is that you have hydrated gum particles on the outside and dry gum on the inside. And so you have, undissolved dry gum floating around in your product. So not only do you not have the viscosity, but you have these particles that don't taste good that are in there. Okay, so that's one way, is to separate those particles by air. There's a couple other ways. We can separate the particles using other things. So we can disperse in something that the gum is not going to dissolve in. So we could disperse it in oil or alcohol. So if we disperse it there, then we can use that solvent to fluff out or separate those particles before we add the water. We can disperse it in a solid, which would just be other ingredients in the food. So that could be salt, sugar, spices, anything like that. So physically separating those particles with something that you would normally add to it anyway. And then finally, we can just use high shear. So you would still want to be careful with the addition of that gum. So for instance, if you had something mixing at a high rate of speed, you could slowly, sift the gum particles into that mixture and not form those fish eyes. So there's 4 ways to disperse these gums. A couple of rules of thumb. Since these gums are hard to dissolve, Sometimes it's tempting to dissolve them hot. You always want to dissolve these in cold water. I should say disperse. So you want to disperse a gum under conditions where it's least soluble. So it's going to be least soluble the colder the water is. And that's because where it's least soluble, it's going to take the longest to hydrate. And so you have the most time to get those particles separated before they're going to swell and stick together. So we want to disperse in cold water, then we heat it to get the functionality that we want. So disperse cold and then heat them up. Very similar to starch, but these are different from starch because we're not in granules and they will dissolve in water. So sometimes, you know, when we work with these gums in the lab, usually we will disperse in cold water and then just keep them stirring for a day. And that will hydrate them also. But in industry, you know, don't want to wait that long because things cost more if they take a long time. So usually they'll disperse in cold and then heat it up. Okay, so now let's look at the viscosity profiles of some of these gums. So first on this slide, we're going to look at viscosity, which has this Greek letter nu, is the symbol for viscosity. And you see the equation up here. But this axis is viscosity. And then on the x-axis, you have shear rate. It's defined up here, shear rate. So basically, this is what happens to the viscosity when I turn a mixer from low up to high. So this A curve here just stays the same. That's a Newtonian fluid. That would be something like water or oil or honey, not polysaccharide gums. But we do have some food examples that are Newtonian fluids. So no matter how hard you mix them, the viscosity stays the same. Then we have this B curve here where the viscosity is high when the shear is off. And then as you start to apply some shear, the viscosity drops. And that's called shear thinning, which usually we'll say pseudoplastic. And this is the curve that polysaccharide gums will follow, almost all of them. So this is the most common for our polysaccharide gums, pseudoplastic. They're going to be shear thinning. So high viscosity, as we start to beat that, it's going to lose its viscosity. We have this C curve, which means that the viscosity increases as we mix harder and harder. So there aren't any food polysaccharides that behave this way. There are a lot of synthetic polymers that are used in other industries that behave this way. But in foods, we don't see this C curve very often, or at all. Well, there's one example, but very rarely do we see it. And then finally, we have this D curve here, which looks just like B, also shear thinning, but it's shifted. And so what this means is you could, if you wanted to, you could draw a straight line here over to this axis. What this is showing is that you have to apply some amount of shear before the viscosity will drop. So the viscosity stays high for a period of time, and then it starts to drop. And that would be characteristic of something that's a plastic. And a plastic just means that it's going to hold its shape. It's going to be like peanut butter. And so that peanut butter is going to stay its shape. And then once you apply some shear, you have to apply enough to actually move it. And this would be the plastic characteristic, and then we have pseudoplastic after that. This amount of shear that you have to apply before you start to get a loss in viscosity, that's called the yield stress. So that portion here at the top of this curve where no change in viscosity, that's the yield stress. And that's a characteristic of plastic dispersions. This graph on the right, I have the same thing. I just want to show two shapes of a curve that you can have for pseudoplastic. You can have one where the viscosity drops really fast as soon as you apply that shear. And then one where the viscosity doesn't drop as quickly. It kind of is slower at losing its viscosity. So that B1 curve would be something that would be short. That's what we would call it, short. And then also you can call it non-slimy. And that's usually what we want. We usually want polysaccharide gums that will lose their viscosity fast. And so they, when you take that product out on a spoon, it's not going to have all these strings coming off of it. It's not going to be gummy. And then in your mouth, it's not going to be gummy because you chew it and it's going to lose that viscosity and it's going to have better characteristics in the mouth. B2, that would be slimy. It's also called stringy. And there's lots of polysaccharide gums that are like that, but it's a less desirable characteristic. Okay, now we're going to look at viscosity again. We're looking still at viscosity on the y-axis, but this time, instead of shear rate, we have time on the x-axis. And our shear rate stays the same. You see, that's this constant blue line in the middle. So this is what happens if we just turn the mixer on and we just keep mixing it at the same rate for a period of time. Does the viscosity stay the same? Does it go down or does it go up? So this red line here, this would be thixotropic. So that means that as we mix that for longer periods of time, that mixture is going to lose its viscosity. And this red line is what most polysaccharide gums, or all polysaccharide gums, follow, is this thixotropic line. This rheopectic line, again, is a characteristic of some polymers, but not really those that we use in food. So most of these are going to lose their viscosity the longer that we mix. And this graph on the right here is showing something called hysteresis. I think we've had that term before when we were talking about water. But what it's showing here, this is showing shear rate and viscosity. And as we mix, we are losing viscosity, so that is pseudoplastic. And then because if this mixture is thixotropic, it's going to take some time to regain that viscosity once we remove the shear. So here we're increasing the shear and we lose viscosity, so it's pseudoplastic. Then when we take away the shear, it's going to regain that viscosity, but it doesn't follow the same path back to the beginning. And That difference there is called hysteresis. And this is a function of polysaccharide gums that exhibit their viscosity by interacting with each other. So almost always this is going to be the case. And that's because once we remove that shear, it takes some time for those polymers to find each other again and form those interactions to get that viscosity back up. Okay, let's look at viscosity as a function of temperature. So down here at the bottom, this would be like when we just dissolve the gum. Remember, we want to dissolve gums at a low temperature. So here our viscosity initially is going to be low. And then we need to heat up that gum in order to get that gum fully hydrated. So as we heat it, that viscosity is going to increase up to a certain point, and then we will start to cool it down. And as we cool it down, it will continue to increase in viscosity until we get back to our starting temperature. And so now we have a fully hydrated gum that displays its maximum viscosity, which is what we want because that's why we're adding it to the food. So we've increased quite a bit by heating it. Most gums are going to need to have this done, in order for them to achieve their full potential for viscosity. This curve on the right in red here, this would be if we've already dissolved the gum and we've already hydrated the gum. What happens if we heat it further? So we start up here at the top, we have some viscosity. If we heat it, it's going to lose its viscosity. So essentially traveling along this part backwards. So it's losing its viscosity. And then if we subject it to too high of a temperature, we can get some degradation. And then we follow this curved line here. And if we've degraded the gum by heating it too much, then when we cool it back down, we have a lower viscosity than before. So ideally, we want to limit ourselves to this point so that we can go back and have the same viscosity we had before. But if we have some degradation, we may end up, after that second heating step, with a lower viscosity than we had before. And then now, finally, we'll look at pH. We have two classes of gums. We have gums that are neutral and gums that are negatively charged, anionic. And neutral polysaccharide gums, and there will be a slide later that will show you exactly which ones are which. But if you have a neutral polysaccharide gum, that would mean that it's comprised of sugars that don't have any charge on them. They just have hydroxyl groups on them. So something like amylose and amylopectin would be neutral polysaccharides. And we can think about neutral polysaccharides in foods as being independent of pH. They're always going to have the same viscosity. Doesn't matter what the pH is. We only have to get really high for that viscosity to drop. And usually we're not getting that high in food. So this only happens when we get really high and we ionize those hydroxyl groups, which is not going to happen in most foods. So you can typically think, if you're working with a neutral polysaccharide, that if you change the pH, the viscosity is not going to change. In contrast, if you have an anionic polysaccharide, one that has some charge on it, then it is going to change as a function of pH. And you would typically think about this side of the curve. So the lower the pH goes, the higher the viscosity will be. You do have to be careful out here at really low pH values, because sometimes at really low pH values, these anionic polysaccharides can precipitate out of solution. So if you have an anionic polysaccharide, what is happening to the charge the lower the pH goes? It's getting neutralized. Excellent. So it's losing its charge. And so the repulsion between polymers goes away. That's why it can precipitate out. So you have here, you have all these polymers that are repelling each other. So of course they're going to stay in solution. But if you neutralize all those negative charges, now they can associate. And that's part of the reason why the viscosity goes up, because we can form more junction zones. But if we neutralize everything, then it can precipitate out, because we form extensive junction zones that actually exclude it from water. Okay, finally, just some bullet points here. Some of these things we've gone over already. This is kind of like a summary slide. So viscosity is a function of the volume swept out by a polysaccharide. So polysaccharide is this long molecule that is floating around in the water. And so if you have a molecule that's very stiff, a polymer that's very stiff, that's going to interact with more water than one that is flexible and can be bunched up like a shoelace. So that long polymer that's very stiff is going to interact with more water and give a higher viscosity than one that is very flexible and can be wadded up and interact with only a little bit of water. And same thing with linear and branched. So a linear molecule is going to interact, of course, with more water than one that is at the same molecular weight but branched. It will be very small. And then here, anionic are generally more viscous than neutral. And we saw that in the last slide, especially at low pH values. All right, so here's this slide we've seen several times now. And just showing gel formation. So the gel formation with polysaccharide gums is going to be the same kind of mechanism that we talked about for starch. We need to disperse those polymers and then allow them to form junction zones to entrap water. What I wanted to add to this slide here is reversible and irreversible gels. So reversible gels are those that when we heat them, the gel will melt, and then as we cool, the gel reforms. So these gels, we can go back and forth between a gel at cold temperature, we heat it up, thins out, we cool it back down, reforms the gel. So most polysaccharide gums are going to behave like this. There are several examples where they don't behave like this. So a lot of times polysaccharides that form a gel as a result of interaction with cations, so these anionic polysaccharides interacting with cations to form a salt bridge. We'll see that in a minute if you're not remembering what that is, but those types of polysaccharides oftentimes will have irreversible gels. So these type of gels, if we, first of all, typically will form them. If you heat them, the gel does not melt. Or when we cool them, the gel does not reform. So if we heat them and the gel doesn't melt, or if it does melt, but then when we cool it, it doesn't reform, then it's irreversible. And so a lot of times those gels that are formed with salt bridges, or there are some cases where gels are formed through covalent linkages, and those are also not reversible. They're also irreversible. A couple of different textures we can have. At the top, we can have a very firm and a brittle gel. So a gel that you can cut with a knife and it will hold its shape. And then at the bottom, we have soft and flexible gels, which if you cut them, they will kind of start to collapse or sag on each other. And then there's a few gelling polysaccharides that are listed there that would have those characteristics. So kappa carrageenan would be more of a firm and a brittle gel. And the combination of xanthan and locust bean gum would be more of a soft, flexible gel. Here are different ways that we can form junction zones with these polysaccharide gums. So we have two here on the left that are using salt bridges to form these gels. So here is two polysaccharides, and then these dots here are cations: calcium, magnesium, zinc, typically a divalent cation here in the center. And so this would be something that would be formed with anionic polysaccharides. So this jagged region here where they're associating with those cations, that portion of the polymer has some negative charge to it. And so this one egg box here, this is just formed with a straight line. Here, sometimes you can have some helical structure interacting with these cations. So I'll give you an example here. This one, the example that would be most common would be a pectin gel. This is a pectin gel. Also could be an alginate gel. We don't use alginate real often in food, but certainly pectin's used a lot. This type of gel here is common with carrageenans. Carrageenans are a negatively charged polymer, and they can form these helices. And then also the negative charges there will interact with cations in the mixture. This aggregated double helix, this would be also a characteristic of carrageenans if you don't have very high ionic strength. So if you don't have very many cations around, then you'll form a gel still with these carrageenans using this aggregated double helix form. And then finally, this one is extended ribbon-like structure. This is a function of neutral polysaccharides. This is how they're going to form their junction zones. So something like a guar gum or a locust bean gum would form junction zones this way. Okay, these are all the gums that we'll talk about, and they are, I feel like, the most commonly used gums. So there are plenty others, but these ones are very commonly used in a lot of different products. Second column, you see their source, where they come from. You know, some of these gums are storage polysaccharides in seeds. Others are produced by microorganisms. Some come from the sea, so lots of different places where these are coming from. Here's where you can note whether they're a neutral polysaccharide or a charged polysaccharide. Here I have branching. As we go through the structures of these, you're going to notice that sometimes the designation here doesn't match with what I say the structure is. And that's because sometimes if the branches are very small, then that polysaccharide gum is still said to be linear because it behaves like a linear polysaccharide. You have to get the branches sufficiently long for it to really behave like something that's branched. So we only have really a few polysaccharide gums that are extensively branched, like amylopectin is. Most of them would be classified as linear even if they have some little short chains on them. And then finally, this functionality column. What you should notice here in this functionality column is that we have a lot of thickening and we have a lot of gel formation listed. Those are the two major functions of these, so that's what we should see. But we don't see that they all do that. So not all of these polysaccharide gums will form gels. So guar gum, the first one listed there, will not form gels. So you wouldn't, if you need to form a gel, you would not use that polysaccharide. And so you have to make sure that you're selecting the right one if you do want gel formation. Okay, here's the first one that we'll talk about, xanthan gum. Xanthan gum is the most widely used polysaccharide gum in the food industry. So number one. So we definitely want to understand functions of xanthan gum. It's very ubiquitous, used in a lot of different things. So this is a linear polysaccharide, even though here I'm showing that it's got a branch on it. But it behaves like a linear polysaccharide. The backbone here is like cellulose. So it has a cellulosic backbone, but then it has this trisaccharide side chain. And it's made up of some mannose and galactose, or glucose, sorry, and some methyl esterification, some uronic acid characteristic to it. So it's kind of a complex side chain. But this side chain can change. So they're not always going to look like this. And so the side chain and the molecular weight will change depending on fermentation condition. So this is a polysaccharide gum that's produced by microbial fermentation of the microorganism called Xanthomonas campestris. And you don't probably need to remember that, but it has xanthan in the name, so it's kind of easy to remember. Xanthomonas campestris makes this. So depending on the strain of Xanthomonas that we use, this side chain is going to differ. And then also depending on the fermentation conditions. So if we change the pH, we change the carbon source, if we change how much oxygen is present, all of these variables are going to change the structure of that xanthan gum, and then it will change slightly the functionality of that xanthan gum. So one xanthan gum is not necessarily going to be exactly the same as another. Xanthan gum is a non-gel forming polysaccharide. So this is only going to form viscous mixtures. So it's going to contribute to viscosity and not gel formation. But it has some unique characteristics of this, this viscous mixture. So one would be that viscosity is almost unchanged from 4 to 60 degrees Celsius. So why would that be an attractive characteristic? Okay, yeah, so for shipping and storage, if there are varying conditions, the product's going to stay the same. So if you imagine that you have a sauce that has some particles in it, if you ship that sauce and let it sit in a warm warehouse, you don't want all those particles settling to the bottom, and then once it gets to the consumer, all those particles are at the bottom. So that would be undesirable. So good. Any other thoughts? So the real advantage of this is that we can serve this straight out of the fridge or at room temperature, and it's going to have the same characteristics. So if you think about like an ice cream topping that you might store in the fridge, you could take it right out of the fridge and pour it, or you could leave it at room temperature and pour it. And it would be about the same. You could even heat it up as long as you don't get above 60, and it would still have that same viscosity. So there's lots of products out there where the consumer may serve this cold, room temperature, or even warm, and you as the manufacturer would want that same viscosity at all those temperatures. And xanthan gum is unique in that it can do that. There aren't any other gums that will do that. Xanthan gum also has a unique characteristic that it can suspend particles I guess I'll just leave it at that. It suspends particles, but then I guess it's very short, I'll say. So if we think about something like a salad dressing that has some parsley in it, maybe some pepper particles in it, xanthan gum can keep those suspended. And you can almost think about it as a plastic. So it's non-gel forming, so it's not a real gel, but with no shear, it's going to be sufficiently viscous to suspend some pretty large particles. But then if we shake that bottle, it's going to lose all that viscosity immediately so we can pour it. So it will suspend those large particles. We just give it a little shake, and it loses all its viscosity, and we can pour it. So that's another really unique characteristic, is that it's very, very short. It loses its viscosity almost immediately upon shear. So another one is that there aren't any enzymes that we use in foods or that occur in foods that will degrade this polysaccharide. And so we don't have to worry about enzymes coming in and breaking this down and destroying our viscosity. Let's see. Okay, I think we've gone over just about everything. It's very stable to heat and pH degradation. So it doesn't hydrolyze very easily. It's stable to heat. So lots of advantages. Okay, so remember here that it's non-gel forming. So there are cases where we're going to form a gel with xanthan in just a minute, but by itself, xanthan is non-gel forming. So we're going to use this in sauces, condiments, dressings. those kinds of things, very common to use xanthan gum. Okay, next we have guar and locust bean gum. These are galactomannans. They're made of mannose backbone here in green. And then we have galactose side chains, just one. So galactose stubs. Still going to behave like a linear polysaccharide. So guar and locust bean gum are very similar, as you can see. They only differ in the pattern of those galactose stubs that come off of the main chain. So guar gum is going to have evenly distributed galactose residues on that chain. And locust bean gum is going to have clumps of galactose stubs, and then regions where there is no branching at all, no galactose units at all, like this. And that's going to change the functionality of these two polysaccharides a lot. So first of all, guar is a viscous polysaccharide. So it's, again, another example of a non-gel forming polysaccharide. It's going to be there to contribute viscosity. So guar gum is easy to disperse. So this means it hydrates slowly. So it's easy to dissolve because it takes so long for it to hydrate. And I'll just say here that it exhibits synergy with xanthan and carrageenan. So if we mix guar gum and xanthan gum together, then we get a more viscous solution than we would predict based on each of those polysaccharides separate. So they interact in some way to have a higher viscosity than what we would predict based on their concentrations. Still only viscous, though. It's also inexpensive. Locust bean gum is much more expensive. So it's going to be used in cases where it's going to have its unique functionality, which is that in combination with xanthan or carrageenan, it will form a gel. So if we mix xanthan and locust bean gum, both of these gums by themselves will not form gels, but if we mix them together, they will form a gel together. Carrageenan forms gels on its own, but if we mix carrageenan and locust bean gum together, then they will exhibit synergy. The gel will be stronger than we would predict based on each one of those separately. So in cases where we want to actually form a gel, that's when we would use that locust bean gum, because it does cost more. Used in milk products, frozen foods, and stuff like that. Okay. This is a picture of that gel. So here is xanthan, and here's locust bean gum. You see this branched region with the galactose units coming off, and then this unbranched region is what interacts with the xanthan gum to form a gel. So this extensively, this region where it's extensively interacting together, forming that junction zone, that's why it forms a gel. So right here, I just wanted to say also happens with carrageenan. With carrageenan and locust bean gum. So not carrageenan with xanthan. Okay, next we'll talk about carrageenan. So carrageenan has this crazy structure here. It's just a bunch of galactose units linked together. But we have, on some of them, we have this internal ring structure, this internal anhydro bond. Every other one, in fact. And then we have sulfate groups attached to it at various places. You see some sulfate groups here. So that's why it's an anionic polysaccharide. So carrageenan, lots of stuff about carrageenan. First, we can talk about this picture here. So this picture is showing these kind of helical structures here. Those are carrageenan. And they form those aggregated helical structures like you see here. And these circles in this picture are casein micelles from milk. And when we mix carrageenan into milk, it will form this structure, and which is a gel structure. So carrageenan will exhibit synergy with casein micelles to form a gel. So carrageenan is really common to use in dairy products. Because it forms a gel with casein. So, you know, yogurts, chocolate milk, any kind of thickened dairy product will often have carrageenan in it. We have several kinds of carrageenan. We have kappa, we have lambda, iota. And most of these are going to form gels. There's one that does not form a gel. Let me get so lambda is the one that doesn't form a gel. So remember this anhydro bond here? This bond? That bond is necessary for the polysaccharide to form a gel. Without this anhydro bond, it cannot form these aggregated triple helices, and it won't gel. And lambda does not have this structure, so it can't form a gel. Also, low pH will hydrolyze I know that's spelled wrong. Just go with it. We'll hydrolyze the anhydro bond. So at low pH, we're going to lose our gel-forming characteristics. And that low pH is anything less than 5. So not even that low. So very susceptible to hydrolysis. And at that low pH, we will lose the ability to form a gel with carrageenans. Usually carrageenans, you know, you have kappa, lambda, and iota. Most of the times, the industrial mix, they're just a mixture of a bunch of these different kinds, and to give certain functionalities. So anyway, I think that means we're out of time now. So used in yeah, a lot of dairy products as well as other things, but it has this unique functionality with dairy products, but not low pH. Okay. Thanks, everyone. We'll continue this on Wednesday.